Hey everybody, welcome to another section of Bed Talks. Hope you're doing well. So today what we're going to be tackling is this end of 16.2 and into 16.3, all covering now the ideas of trying to find integrals over vector fields, line integrals over vector fields. So the first thing we wanted you to do, especially in this video, to kind of understand going forward what we're talking about, we're going to be dealing with this certain type of integral that looks something like this. And what does this actually mean, right? I have this vector field f, and what does this r mean? This is a curve, that my parameterization of this curve c. And what does this actually physically mean? So I want you to kind of imagine this. Imagine if I had a wind tunnel over there. I said this wind tunnel that is coming towards me, and I want to find out how much effort it would take for me to move from here to that fan. I hope you'd agree that as I go farther in this direction here, as I go farther and closer to that fan, it's going to be harder and harder for me to move. So I'm going to have to put a lot of effort into going to that fan. If I go the exact opposite way, it's helping me because I'm going in that direction. So it's going to be a little bit easier for me to be going in this direction because the fan is pushing me in this direction. You can imagine that fan as my vector field f, this wind tunnel. Or you can kind of imagine that I'm trying to push an object in this vector field. So imagine I have this interesting vector field here. Doesn't have to be anything crazy. I'm not trying to make this crazy at all. Just kind of an interesting one, which is possible. And imagine I had a point, this is my vector field f, I'll name this vector field f, and my vector field f, and I have this curve right here. Let's say from here to here. I'll name this point A and I'll name this point B. And let's say I go from A to B. And I want to find out how much effort it takes for me to move an object from A to B. Well, let's kind of go back to think about how much work it takes. What is the idea of work, right? The idea of work, as we saw, is the kind of the force that I'm pushing on an object with the dot product of the displacement vector. So in some way, right, we have this idea, right? If I just had an object and I'm trying to figure out how much, like if I have this object here and I'm trying to move it in this direction and I'm pushing on it with this force here, right? We can kind of see that the only force that I'm really worried about is the force that is, horizontally pushing the object in that direction. So that's why I take the dot product. And in this case, right, we saw this back in chapter 12 when we were doing this, that work here, if it was positive, was helping it, like pushing it in that direction. If it was negative, we're going against the grain here. So what I'm trying to say here is I'm trying to move this object from A to B. Now, this displacement vector, we thought of this as just a linear vector, right? This was thinking of it in this time where I was just going from A to B in this line. Now, I have this curve here. It's not a linear vector. So how do I come up with that? Well, again, we're going to think about the idea of the dot product here. So this displacement vector, I hope you'd agree, this displacement vector maybe would be going in this direction, right? I'm trying to move from point A to point B, maybe here. This displacement vector is also tangential to where I need to be going. And so maybe we can start to think about that the amount of work done necessary for me to move A to B is kind of the sum of all of the force vectors that I have here with the tangential vector that I'm going on, like the derivative at that point. So let me just draw something here. So take this point right here. I hope you'd agree that the tangential vector, this tangential vector t, right there, something like that. I'm going to even zoom in here just so we can kind of see this more. This tangential vector t here, I'm going in this direction. I'm moving an object from A to B. And then I also have this force field. I'll name this the blue force field. I have this force field here. So if I take, in this case, I have this vector f, which is pushing me in that direction. I have this tangential vector t, which I'm trying to move this object from A to B across. And what's nice here is if I take f dot t here, this one specifically, they're an acute angle. They're at an acute angle right now. So think about that. Would that be a positive value? Would that be a negative value, or so on, right? In this case, since it's acute, this is going to be positive, right? Because I'm going with the curve. I'm going with the vector field. So the vector field is actually helping me move the object. And so because of that, if I have f dot t here, at this point, the work is going to be positive. If I was going the exact opposite way and maybe flipped this and going the exact opposite way here and making this green vector the exact opposite way, this angle would then be negative. So if this is positive, right, we kind of think about this is going to be the work going with the flow. We kind of say this, we're going with the vector field. If I have f dot t, being negative, imagine if I move this object from B to A. You can kind of see that I would be pushing against this wind. So the work here, I'll be going against. And lastly here, imagine if I'm exactly orthogonal. If I'm exactly orthogonal here, which means that at some point, maybe I'm going directly perpendicular to the vector field, the work is going to be 0 because it's going to be half kind of working with me, half working against me. So the idea here, if you want to think about it, if I'm moving from A to B, I'm taking f dot t, I'm taking all these f dot t's, all these possibilities, and I'm summing all of them up at every single point, right? What I'm doing here is when I see down here, maybe I'm going in this direction, and my vector field here is in this direction here, my vector field, and then maybe I'm taking something up here, right? And my vector field's maybe moving here, and I have my tangent vector just going in this way. And what we're doing is we're taking the dot product of every single one of these instances, where I take the tangential vector and I take this force vector. And what I'm going to do is I'm going to add all them up. And how do I add all of them up? Well, I just integrate, right? Because that's the idea of an infinite sum, right? Because I have an infinite sum here. If I'm adding all of them up, that's the same thing as integrating. So what you can kind of imagine is if I was to calculate this integral, I would actually calculate this. I'm going to call this curve C. It's really the integral of f dot t ds, where ds here is, again, just my arc length in this case. Now, what's really, really nice is from this point, what we can do is remind ourselves, if I want to convert this and actually evaluate this integral, right? This is actually a work integral, right? This is what this is saying. This is the amount of work that it takes to move an object along a curve C through a vector field F. This is actually what this physically means. Now, what we wanted to do instead here is, it's very hard to evaluate ds, right? So what we do, again, is we can go ahead and parameterize our curve C. We can go ahead and try to evaluate these things and evaluate the function, the vector field at my R of t. And so now we imagine here, I'm going to kind of move up here now and kind of see how we can get back to this. So as a reminder, if I parameterize my curve R of t, as a reminder, the tangential vector then is equal to the derivative of that divided by the magnitude, because this is the unit tangent vector. It's the unit tangent vector at every single point. And as a reminder, we exchange this ds, we usually exchange this for the magnitude of r prime of t dt. And so writing all of this here, we can actually come back, which is pretty interesting, to now evaluate this as, if we go ahead and do this, the integral from a to b, let's say, of f at r of t, right? What I'm going to do now is I'm going to parameterize my r of t. I'm going to plug in wherever we see x and y to my vector field f. And I'm going to evaluate this f of r of t. And then I take the dot product here. This is the dot product, right? Because I'm thinking about work. So I take the dot product with, well, I know the tangential vector is now this guy, r prime of t over the magnitude of r prime of t. And then I have to change this ds to the magnitude of r prime of t. So go to the magnitude of r prime of t dt. And what's nice here, I hope you'd see, is that these will cancel. And I'm left with f at r of t, the dot product of r prime of t dt. And what we also like to do here, we can write this as a shorthand, if we would like, as f dotted with dr. And this right here is, again, the concept of we try to write this is a work integral. Or maybe as we come forward, as we go farther, we might think about this maybe as a flux integral. But in this case, we'll think about this as a work integral. This tells me the amount of work it takes to move an object along a curve C through a vector field F with a parameterization R. And what we can do now is we can come up with a lot of different things. Now, I want to be very, very careful here. When we were thinking about this in this integral last chapter, this guy, we were very conscious of the fact that C did not depend on orientation, right? Because we're coming up with a, you know, a sheet, right? This was an area. So it didn't matter if I was going positive or negative here. However, in this case, it's actually going to be very important for us to think about this, as it is very important for the orientation, because I hope you'd agree, if I go from A to B here, the amount of work it takes for me to move now to point A to B will be positive, because I'm going with the curve. If I'm going in the exact opposite direction, it should be negative, because I should be going in the exact opposite way. So what we can find, just as a reminder here, we can find that if I go in the exact opposite direction, it is going to be negated. So the amount of work it takes for me to move an object from A to B is the exact same as the negative of the amount of work it takes for me to move from B to A. And this is just an important kind of thing. I don't know why this is popping up, so I'm sorry about that. So in this case, that's what we're kind of talking about here. And this is an important relationship to make. So it's a really important orientation here. How do we go from point A to point B is really important. And this way to evaluate this integral is exactly what we need to do. And it's the exact same process, actually, as evaluating this. We parameterize our curve. We evaluate r prime of t. In this case, we need r prime of t, not the magnitude, right? Because I need to take a dot product, because this is a vector, right? So I need to get to be a scalar, right? I need to get to be a scalar here. So I need to take a dot product here. Instead of this case, I actually took the magnitude of r prime of t. In this case, I'm taking r prime of t here. So now, let's kind of go forward. I'm trying to do a problem here and try to see what this actually is saying. So I have a problem here, which is the integral, yeah. So I have this integral here, f dot dr, where f here is equal to x squared minus xy, and where our curve C is given by the circle of radius 2 from 2, 0 to 0, 2, counterclockwise. Okay. So let's kind of think about this. I have this vector field F. I want to figure out how much work it takes to move an object along the circle of radius 2 from 2, 0 to 0, 2 counterclockwise. So what we want to do is just make sure we understand what's happening here. We never have to really draw out the vector field. It doesn't really have to happen. But I have this point here, 0, 2, 2, 0. I have this point, 0, 2. I'm going along this curve here, along this circle. And I'm going in this direction specifically. And I want to figure out how much work it takes to move an object. Now, in order to do this, it's the same exact process as we did in the past. What we do, first off, we parameterize our curve. Parameterize C. So we have a circle. We can again parameterize this with cosines and sines. We have to be careful though, because of our radius here. So our radius is 2. So we can parameterize our curve as 2 cosine of t and 2 sine of t, because I'm moving counterclockwise, so I can do that. So r of t here can be written then as 2 cosine of t, 2 sine of t. And we have to come up with a parametrization domain. And since I'm going from here to here, right, this is really theta being 0, and this is really theta being pi over 2. So I can say that t would be just between 0 and pi over 2. Okay, so this is my parameterization. 2 now. As you can see here, if I'm coming back and needing to evaluate this, right, I need r prime of t. I don't need the magnitude, so I only have to calculate r prime of t. So let's do that. So calculate r prime of t. And doing this is not too bad here. R prime of t is equal to negative 2 sine of t, 2 cosine of t. The next thing we need to do, kind of zooming out here, we need to evaluate f at r of t. And in order to do that, Wherever I see an x, I plug in 2 cosine of t. Wherever I see y, I plug in 2 sine of t. So I evaluate this, and I will get, well, x here is x squared. I will get 2 cosine of t squared. And then this is negative x times y. So negative 2 cosine of t times 2 sine of t. And we can kind of simplify this a little bit and get 4 cosine squared of t, negative 4 cosine of t sine of t. And this is my evaluation of f of r of t here. Okay, so then the last thing we need to do right before this, right, if you see here, we need to take the dot product. I usually like to do the dot product outside of the integral because then I can like rearrange it to how I want to when I evaluate it in there. That's usually what I suggest doing. You can go ahead and just evaluate the integral if you want by keeping the dot product in. It's totally up to you. I like to do it outside so that I have a little bit more room. I'm now going to take the dot product. And the dot product here is going to be 4 cosine of 2t times negative 2 sine of t. 4 cosine squared of t times negative 2 sine of t plus negative 4 cosine of t times sine of t times 2 cosine of t. Times 2 cosine of t. And can we simplify this a bit? Yes, we can, because this is actually the same thing on both sides, which is kind of nice. So if you see here, this is a negative 8 cosine squared t sine t. This over here is the same thing. So we can just combine it to get negative 16 cosine squared t sine of t. And this is now my integrand, which I think is pretty nice, honestly. Because now what we can do is our step 5, and the fun one is just evaluate the integral. And again here, it's okay if the answer is negative, if it does come out to be negative, which I think it will here, seemingly. It seems like it will. So the integral here becomes a to b, well, in this case, a, we have from 0 to 2, so pi over 2. We then have this integrand, which is negative 16 cosine squared of t sine of t dt. And from here, what we can do is, to evaluate this integral, we can use u sub, right? I would usually let u be equal to cosine of t. Du is equal to negative sine of t, which is nice. So this will come out to be then the integral from 0, the integral just of 16 u squared du, because the negative will go away because of my du here. Where that? Then this will become, I kind of do this 16 thirds u to the third, evaluate it between, well, I need to plug this back in now, 16 thirds times cosine to the third of t, evaluate between 0 and pi over 2. That's that. And here, cosine of pi over 2 is 0, so that would become a 0. And then cosine to the third of this would be just 1. So because cosine of 0 is just, cosine of 0 is just 0. Cosine of 0 is 1, and so 1 to the third is just 1. So I'm left with negative 16 thirds. So let's think about this really quickly. What is this saying? Right? What is this actually saying? This is saying here that given this curve and this vector field, if I move an object from here to here along this curve, because this is negative, that means I'm going to be going against the vector field here. I have to put in more work to move an object from point A to point B. And this is a really important idea to make sure that it's okay for this physically to make sense. So this means that a lot of the vectors might be, like coming down on it like this, right? That means a lot of the vector field might be coming down on it like that, and to move an object this way. So if I went from the exact opposite direction, We can just change this from a negative to a positive. It would be just 16/3. So that's also a really nice thing. So if you're asked the question, do both ways, you'll have to do it one way and then flip the answer, which is cool. That's kind of how we do it. So again, the process is the same as always. Parameterize your curve C as R of t, calculate R prime of t, calculate what the vector field is on the line R of t, and then take the dot product and then evaluate your integral. It's usually the very standard way of doing it. So that's kind of the way you would go about doing these kinds of problems here. And just as a reminder, you might see integrals here written a little bit differently. You might see these integrals also in this form, where you might see something like p dx plus q dy. Something here, like that. And if you have something like this, you know, this is totally okay to be able to evaluate something like this here. And you can think about this exact same way. This is kind of like dot product-y thing. I hope you'd agree, right? Because I can maybe rewrite this, if you'd agree, as PQ dotted with dx dy, right? Something like that. And even more formally, if I parameterize this curve, as a reminder, how do I think about dx and how do I think about dy, right? How do I think about those? Well, as a reminder, what we did in the last video was we saw that we can replace dx with x prime of t dt. We're going to replace dy with y prime of t dt. This can be written actually as something, I'm going to keep this curve here at the moment as p times x prime of t dt plus q y prime of t dt. And what's cool here is this becomes px prime of t plus q times y prime of t dt. Now, in this case right here, I can actually write this as a dot product. PQ dotted with x prime of t, y prime of t. And what's even better is this right here is my f, and this right here is my dr in this case. And so because of this, t r of t, we'll say that this is evaluated at r of t now, dotted with, this actually is the definition of r prime of t, dotted with that, dt. And so this is the exact same thing as a work integral, because what I'm saying is I'm moving along this curve C with a vector field PQ. So if you ever see something like this, you can kind of convert it in some way to a vector field idea. It's just an important thing to remember. So if you think about this, if you're trying to understand what p dx plus q dy actually means, you just say, okay, I have a vector field PQ. That's my vector field. I'm just trying to go with that. I'm trying to evaluate that. Here. Okay. I'm trying to evaluate how much work it takes to move an object. The next thing I'm going to talk about here is so I've kind of finished with 16.2, and now you might say to yourself, and this is actually a really good question to start to ask yourself here. I have these integrals. And I think it's a really, really interesting question here of asking, if I have a vector field, are there any types of vector fields that, regardless of path, will cause me to have the same amount of work to get from A to B, regardless of how I get there? So let me kind of explain what I'm saying here. Is there a type of, let's say I have this point A and I have this point B. I want to know what types of vector fields. I can go in all these different ways. All these different ways here to get from there. I want to know, is there types of vector fields such that regardless of how I get from A to B, this answer is always the same? And it's not really too obvious of an answer, right? You would think that there might be some vector fields that do that, but a lot of times they won't be. But you can kind of imagine that gravity, I hope you'd agree, is if that's a vector field, it doesn't matter how you get from point A to point B, it's going to be the same amount of work it takes. For instance, right, gravity here, the amount of work it takes for me to move, let's go 3 stories above my building here, all the way to the roof. If I take the stairs, I could take the stairs to get to that point, to get to the parking lot upstairs. I could also go, up the elevator, go down the road, up the elevator and all the way over to my point there. I can also just go and drive for a while and then come back and go back up. Because gravity there is kind of, we call this a weird vector field because, gravity is conservative in that way, right? It doesn't matter how I get from point A to point B. I'm still increasing the same amount of height. I still have to go against the grain enough. Even if I go down, I'll have to go back up and it's gonna be the same amount that way. So I kind of just gave the game away there by saying a word called conservative. And what this really is saying is, what's interesting is if I have a conservative vector field, reminding yourself with that actually more it is in 2 seconds. If I have a conservative vector field, this can actually be the same for any curve between 2 points. If I have a point A and a point B, it does not matter how I get from point A to point B. It is path independent. And what we can find is if I have a vector field F that it is a conservative vector field. Again, a conservative vector field is where I have a potential function phi such that the gradient of that function is equal to my vector field. It does not matter, and I repeat, it does not matter how I get from point A to point B. All that matters is where I start and where I end. Now let's think about why this might be the case. Well, I'm not going to go through the full proof because you've already done it in your class, but I kind of want to just harken back to something. Recall that I had here. If I have A to B of f of x dx, and I told you that, let me actually go a little bit better, f prime of x dx. If I told you this, if I told you that I have the integral from A to B of f prime of x dx, how would I go about doing that? Well, the fundamental theorem of calculus said, well, I know what the antiderivative of this is, right? I know what the antiderivative of this, it's just f. And so all I have to do is evaluate f at the end point, subtract from the f at the beginning point. This was the fundamental theorem of calculus, the FTC, right? If I'm going from point A to point B, and I'm trying to figure out the area under this curve of f prime of x, all I had to do was, honestly, just calculate where I start and where I ended at that function, height. And this gave me a really interesting idea of how to just evaluate these integrals, right? This was the fundamental theorem of calculus. So now, in this exact same way, well, I now tell you this kind of aspect here, where the function, the vector field f, is kind of related to the derivatives with respect to x and with respect to y. And so what I can kind of say is I want to evaluate, I have the gradient of phi dot dr. If I have something like this, and I tell you that c, is parameterized by r of t, okay? I have to kind of do this, just kind of say, let's say c is parameterized by r of t from A to B. Well, all that really matters, you can kind of think about this as the derivative, right? And if I integrate this, I should just get back phi and only worry about where I end and where I start. And in the same exact manner here, this is kind of a derivative, this is kind of a derivative. What we can do is we can kind of say, I only have to evaluate the potential function at my endpoint minus my potential function at the starting point. And this right here is called the fundamental theorem of line integrals. And it has a very, very, very beautiful parallel to this. And I wanted to say something really quickly. This is actually the same thing as this, just generalized. The fundamental theorem of line integrals is the same exact idea as the fundamental theorem of calculus. This is just a much more generalized version of it. Because if I made this one-dimensional, this would just become dx, and this would just become f of phi sub x, which would get back down to here, just on my line, dx. It's the same thing. It is honestly the exact same thing. So what this tells me now is if I have a conservative vector field, it does not matter how I get from point A to point B. It doesn't. What matters here specifically is that where I end and where I start. I subtract the phi from where I end at. I evaluate that function phi, and I subtract from the function phi at where I started from. So how do we actually utilize this? So this is called the fundamental theorem of line integrals. It's a beautiful and really, really important theorem, because a lot of times your curve C will be incredibly difficult. But if you know that your vector field is conservative, you can pick any path you want. And more specifically, all you have to worry about is where I end and where I start. So let's kind of work on this. So I have a problem here. We're gonna go through this process. Now, the first thing you need to know is, how do I show that a vector field is conservative? Right, if I give you a vector field that's conservative, how do you know, right? How do you know unless you find the potential function, right? You can just find the potential function, but that might be very tedious and might be just not good to do, because it might take me a very long time, or it might be impossible to, because it might not be conservative. So how do you find that a vector field is conservative? So if I tell you that a vector field is PQ, something like this. If I tell you this vector field is conservative, well, how can I find out if this is conservative? Well, let's assume then, briefly, I'm going to use here, if it is conservative, this means that this is equal to a gradient of a function. Specifically, this would be fx, fy. Right? So if this is true, I hope you would agree that P would have to be f sub x, and Q would have to be f sub y. If this is true. So in order to test if this is actually possible, you might say to yourself, well, how can I find out if this actually is possible? Can it be possible that a function with respect to x is equal to P and a function with respect to y would be equal to Q? Let's assume that everything's continuous. What do you know has to be the same, right? We know that the mixed partial derivatives, if everything is continuous, this always has to be the same. fxy has to be equal to fyx. If it's not the same, then we know something's wrong. And so what we can do here is say, okay, well, if I want to get to fxy, you're going to say, okay, well, I want to get to fxy here. So let's take this derivative with respect to y. If I go over here and I want this with respect to x, let's see if we can take this derivative with respect to x. And so now I know that these two guys have to be equivalent. So if these guys are equivalent, that's as good as saying that the vector field is conservative, because if py is equal to qx, that means the mixed partial derivatives of my potential function are the same, which means that I've come from a potential function, because this only happens if I stem from a potential function. And that's really beautiful here. And so this is their conservativity criteria. If py is equal to qx, if your x component is with a derivative with respect to y, and your q component is derivative with respect to x, if they're equal, that means my vector field f is a conservative vector field, and thus there is a potential function such that the gradient of it is equal to my vector field. Let's do a problem. I have this problem here where I have this vector field f of xy is equal to 3 plus 2xy, and I have x squared minus 3y squared. Yep, something like this. Okay, and my first goal here, my ultimate goal here, is to be able to evaluate this. F dot dr, where r of t is given by e to the t sine of t, e to the t cosine of t between 0 and 1. This is my problem here that I have, and I'm currently writing slanted, and I will not be doing that again. So think about the process you would have to use just regularly. Okay, just regularly. What we would have to do is we parameterize this curve C. We then have to take the derivative of this. I hope you'd agree this would then include some interesting integration by, product rule here. So the derivative would be very long. I'll then have to evaluate f at each one of these. get a little bit complicated here, especially with the squared kind of aspect there. And then take the dot product of these two vectors and evaluate them between 0 and 1. It seems like that would be really tedious here. Especially if I have e to the t sine of t, I might have to, this integral, I might have to do some weird integration by parts things. This would become really complicated really quickly. It would. So it would be helpful to find out that it doesn't matter how I go along this curve. I might just want to figure out how I start and where I end. That might not be a bad thing. But in order to do that, I need to figure out if this vector field is conservative or not. So the first thing you should do to yourself is, okay, check if this vector field is conservative. So if this vector field is conservative, I have that p is equal to 3 plus 2xy. I have that q is equal to x squared minus 3y squared. You can kind of imagine like this, if this is fx, if this is fy, are these fx and fy? Well, I'm going to take this derivative with respect to y. And this derivative with respect to y is just 2x. This derivative now I take with respect to x. This whole thing goes away, so this becomes 2x. And so because py is equal to qx, we can then say that f is conservative. And therefore, there is a potential function, f, such that the gradient of that scalar function is equal to the vector field f. Okay, this is great, because now I can utilize the fundamental theorem of line integrals. All I care about now, strictly, all I care about is if I'm going from point A to point B. I'm trying to figure out where point B is, where point A is, dependent on this f. But now I need to come up with that f. How do I do that, right? So there's a couple different techniques you're able to do. I have a certain technique that I like. I can also show you, I'll show you two techniques to be able to find this potential function. You can pick whichever one you would like. I like my first one because I like more of a process instead of kind of looking at it a little bit wishy-washy, but this is up to you. Honestly, it's up to you. So I tell you now that I know that f is equal to the gradient of f. And I know that this has to be equal to, 3 plus 2xy at x squared minus 3y squared. So this means that this, I know that fx has to be equal to 3 plus 2xy. And I know that fy has to be equal to x squared minus 3y squared. This has to happen. The derivative of this function with respect to x has to be this. The derivative with respect to y has to be this. Because I know that this is the gradient. It has to be looking like that. So we want to get my potential. We want to gain that potential function back. So what I would suggest doing is taking one of these guys. Just take one of these functions, whichever one you would like, and integrate it with respect to the variable that that I just took the derivative of. So in this case, if I want to get back up to my original function, I've taken the derivative with respect to x. Let me integrate it with respect to x. So I'm just going to integrate this function, 3 plus 2xy dx. I'm just going to integrate this, okay? If I integrate this, this becomes 3x plus x squared times y. This is a regular integration. However, I now need to be very careful. You might say to yourself, well, why? This should be it, right? This is the answer. You have to be very careful. Now, why is that? Well, when I just integrate regularly, right? Well, if I have one variable, you always have this integration of constant, right? You have this integration constant, right? When I integrate x, for instance, dx, just regularly, right? This becomes x squared over 2 plus some constant c. Now, the thing is, when I integrate, we let y be a constant. So if you'd agree, there might be some constants over here. Yeah, there might be some constants, but more formally, there might be a function of y over here. Because when I take the derivative with respect to x, that entire function would go away. Right? It would have to go away. Because when I take it, I let that be a constant and that would go away. So what this means is there is this function of y that is missing. When I take this derivative with respect to x now, I would get back to here because this is just strictly a function of y. And so in order to do this, to solve this out, we need to know what that function of y is. Now, how do we do that? How do we find what this function of y is? Well, here's the process you can do in two ways. Okay. I'm gonna just go process one, strategy one. Yeah, I guess first way. Okay, my first way here is I have this other piece of information. I know that fy, the derivative of this function with respect to y, has to be this. So what I'm going to do is I'm actually going to take the derivative here. Take the derivative with respect to x here, with respect to y here, and equate it to that. So the derivative of this function with respect to y now, this goes away. This becomes x squared. And this becomes just g prime of y. It's whatever the derivative of that is. And I know for a fact that this guy has to be equal to this guy. So therefore, this has to be equal to x squared minus 3y squared. And so if I see this, what would g prime of y have to be? I'm trying to find g of y. That's the only goal now. And my goal, I see here that this would be g prime of y, right? And in order to do this, g prime of y would then be equal to negative 3y squared, because the x squareds would cancel. So this means that g prime of y is equal to negative 3y squared. And now I integrate that. And this g of y here, if I integrate this, would then become, I go ahead and do this, this will become negative y to the third. Now, you might say to yourself, is there a plus k? You're absolutely right. There really is this plus, I'll let this number be k here. There's some constant, right? There's some constant that comes with this. And so because of this, we can then say that our potential function then, our actual potential function, is 3x plus x squared y minus y to the third plus k. Now, this constant k, I want you to be very careful here. It does not matter what you pick. I'll show you why in a little bit, but it does not matter what you pick at all, honestly. You can pick whatever number you want. Usually, it's very customary to pick this as 0. So I'm going to let this be 0 at the moment. Okay, let this k be 0. So this is a potential function. All you have to find is a potential function. There are infinitely many, because I can pick any constant I would like. But in this case, I'm going to let k be 0, because we usually do, because it's going to go away when I subtract the 2. So it's going to go away. It's fine. So with this in mind then, okay, with this in mind, this is my potential function. Now, what's the second way you could have done it? The second way you could have done it is say, okay, well, let me integrate this guy too. I go down here, I still get this. And then the second way, I can integrate with respect to y now and this one. So what I could do, if I integrate this with respect to y, this becomes x squared times y minus y to the third, plus some function of x now. I'm not going to use g, some function of x, because when I integrate with respect to y, I gain a function of x over there. And now what you do is you take this function right here and this guy right here. And what you kind of do is you do a matching. These two must be the same. And so you note that, okay, they share x squared times y. I'm missing the g of y here, which is negative y to the third. I'm missing the h of x here to be 3x. And kind of matching up what you're missing here gives you kind of what you need to add everywhere. So you see that the missing link here would be negative y to the third. You see the missing link here would be 3x. And so therefore you would get something like this. That's the second way you were able to do it. I like this method better, and the reason why, and I'll tell you, is it gives you a process to go about it, and it makes a little bit more sense. I'm now a hunter trying to find g prime, right? That's kind of what I'm doing, and so this gives me kind of a technique to do that. So this is my potential function. So what did I just do? Right? We're not done with this problem yet, unfortunately. Still have a little more time. So what have I done? I have seen that I'm trying to evaluate how much work it takes to move an object along this curve C. I've found that this vector field is conservative. This vector field being conservative means that, how would I find it was conservative? That Py is equal to Qx. And so what does it mean? This means that I have a function f, a potential function f, such that the gradient of that is equal to my vector field. To be able to find that, I go through this process, kind of setting fx to be the x component, fy to be the y component, going through the process here, and getting this function f of xy. Getting this function f of xy, I now have my potential function. My potential function is this guy. So now, what do I do? The fundamental theorem of line integrals now says the following. Okay? The fundamental theorem of line integrals now says, because of all of this, I'm going to come down here, that this integral right here, cf.dr, the fundamental theorem of line integrals now says, I just evaluate this function, this f here, at my end point and at my starting point. That's all I need to do. So what we need to do more formally is we need to find what r at my end point and r at my beginning point are. Going back here, we are given what r of t is. So my end point, kind of coming back here, this is my curve. So where was I going from? Well, my end point here was r of 1, right? My end point here is r of 1. Doing this, I plug this in. R1 would be, well, I'm sorry, I was going from 0 to pi. That's why this was kind of weird. Sorry. My bad. Let's make this pi. That's what every baker would say. Let's make this pi. So here, if I'm going from 0 to pi, my end point here is from pi. Okay. I plug in pi here, I will get e to the pi sine of pi, e to the pi cosine of pi. And we would get here that this point, well, sine of pi is 0, so this entire thing is 0. Over here, cosine of pi is -1. So this would be negative e to the pi. So this is my end point. This honestly is my end point, a 0, negative e to the pi. How about my starting point? If I plug in my starting point here, this will just become e to the 0, sine of 0, and then e to the 0, cosine of 0. This whole thing again would become a 0. This thing right here would become a 1, because cosine of 0 is 1, and e to the 0 is 1. So this becomes 0, 1. So this is what this says. I am going from 0, negative e to the pi. I'm going from 0 to 1. I'm going from this point right here, 0, 1, to 0 e to the to negative e to the pi. And what it's now saying is, it does not matter how I got there, right? If I draw this out, it's my x and this is my y. 0, 1 is right here. 0 e to the negative pi is something down here, something like this. It does not matter what path I took. I have no idea what path I took. Right? I don't know what path I took, honestly. I don't know. I could take any path from here to here. It does not matter. All that I worry about is where I ended and where I started. And I ended here and I started here. And so therefore, this integral right here, I'm just trying to evaluate my function at 0, negative e to the pi, minus f at 0, 1. And I have this now. And it's not too bad. So let's go ahead and do that. All these x's will be 0 for every single one of these. So f at 0 e to the negative e to the pi, this would be 0. This would also be 0. And this would become negative e to the pi to the third, something like that, minus 0 again, plus 0 again, and then the 1 here would be just minus 1. So this part right here, this negative would stay, because as negative to the third would be negative 1, right? That would kind of stay there. So this whole thing is going to be positive. So I would have e to the 3 pi, because I multiply exponents, plus 1. And that is my answer. Phew, okay. Kind of a long one, I know. But this is kind of the process you need to take in order to do this. So we saw that the vector field was conservative. All we had to do was find our potential function and evaluate the potential function at the endpoint and the starting point. And that's what we did. We took this function and we plugged in x for 0 and y's for these two values and subtracted them and get our answer. That's our answer. Now, if I put a k here as a reminder, if I put some k here, you can imagine that if I did that, I would put a plus k here, as like a plus k here, I'll put a plus k here, and these k's would cancel too because they're being subtracted from each other. So it does not matter what I really did there. It wouldn't matter at all if I plugged in just any k because they would just subtract each other off. They would just go away. So usually that's why we make this 0 to make everything a little bit nicer. And this is the problem that we kind of had. We do that. So the last thing I want to just say here is, what does the fundamental theorem of calculus, fundamental theorem of line integrals say about, well, something really, really interesting here? Well, we have that over a closed C, if I have something like this, as a reminder, minus phi of R of A. And I have something like this. Now, what happens if I'm in a conservative vector field and I have a closed loop? What if I start and end at this point? What if I start and end at that point? Well, if I start and end at a certain point, I hope you'd agree that R of A here would be equal to R of B, which means that wherever I'm with this parametrization, if this is going from A to B, kind of going around this trajectory here, if I start and end at the same point, this has to reflect that. So if that does that, well, what I could do then here is say, okay, well, this is just R of B minus phi at R of B. Just replace this. Because if R of A is equal to R of B if I have a closed curve. And what's really amazing is that this is 0. So what does this say? And this is a really, really important thing to kind of finish off this lesson here. If I have a conservative vector field, and I have a closed simple loop here, really, closed loop. Closed and smooth curve. And I want to find out how much work it takes for me to move an object around a closed curve. If you are in a conservative vector field, it does not matter. This will always be equal to 0. Where C is closed and F is conservative. So if we have a conservative vector field, and I go in a closed loop, automatically your answer is 0 for how much work it takes to move an object. There's an equal amount of work being done against you and work being done helping you here. And that's the main goal of this. So the fundamental theorem of line integrals is a kind of a beautiful thing, which kind of represents a lot of things in multi-dimensions. And it allows us to evaluate line integrals and evaluate these really, really complex problems really nicely, honestly. If I have a really complicated curve, I can get rid of the curve. It becomes path independent. And specifically here, if I have a closed curve, really, really quickly from the fundamental theorem of line integrals, I'm ending and starting at the same point, so the potential function at those points better be the same. And so there has to be 0. And so if you ever have a conservative vector field, immediately, if you have a closed loop, it's 0. And that's kind of the process here. So kind of zooming out, seeing what we did here. We did a lot in this one video. It's probably a little bit long. But it's a really important thing to kind of talk about each one of these parts, to be able to evaluate this work integral that we're going to be tackling a lot. This work integral is really, really important because this process to be able to evaluate this, there's a lot of different ways we're able to. And you might be saying to yourself, how do I know which process to use at which time? How do I know which one it is? We'll talk about that going forward, especially after the next section. We'll kind of draw out a full schematic of all the processes we have to evaluate this kind of thing. Okay, so that's the process here. If you have any questions, let me know. And I hope you guys are doing well. And vector calc is cool, I promise. I'll be a little bit tough. I know it is, but it's really, really awesome. So keep going with it. And let me know if you have any questions. Have a great day, guys.